Dear students, I welcome you all to this problem solution series in digital electronics. I am solving the problems from the book Digital Design by Maurice Mano and Michael Sileti. So in this video, I am solving the problem number 5.19 from the chapter number 5. The problem is a sequential circuit has three flip-flops A, B and C. These are the three flip-flops. One input is X in, okay, this input is denoted by this X underscore in, and one output is Y out. The state diagram is shown in figure P 5.19. Okay, so this is the given figure P 5.19. Here we have a state diagram. The circuit is to be designed by treating the unused states as don't care conditions. Here we have few states, that is from 000 to 100, and we will have few unused states, and we have to consider those unused states as don't care conditions. Then we have to analyze the circuit obtained from the design to determine the effect of the unused states. So while designing the circuit, we have to use D flip-flops in the first part, and in the second part we have to find out the JK flip-flops in the design. Here we can see that for D flip-flops, the input and the output are the same. Here we can directly take the D inputs as the next state output of the flip-flops. So first of all, we have to find out the state table, and after finding out the state table, using K-map, we have to find out the state equation, and after finding the state equation, we will draw the logic circuit. So here we'll have this present state A, B and C. These are for the three flip-flops, okay, and the input is X. The next states are written as A of t plus 1 is the next state for A, B of t plus 1 is the next state of B, and C of t plus 1 is the next state of C, and Y is the output. So we have to consider these four variables, okay, as the inputs, and then we'll find out the next state and the output using the state diagram. So for four variables, we'll have 0 0 0 0 0 0 0 1. Okay, so this is nothing but for the present state 0 0 0, input 0 and 1. Okay, so we'll see the next state and the output. Next we'll have 0 0 1 0 0 0 1 1. Okay, this means we have the state is, we have the present state is 0 0 1, and for input 0 and 1 we have to find out the next state and the output. Next we'll have 0 1 0 0 0 1 0 1. Okay, here also same. Next we'll have 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1. So up to here we have to find out, because you can see that in the state diagram up to 100 we have. Okay, so for this 100 we have find out the input. For 0 and 1 we have to find out the next state and output. So in the question it is given that we have to consider all the remaining, that is after this 1001 we will have 1010 1011, like that up to 15 we will have to use don't care condition. We have to use don't care condition, that is D of A, B, C. These are the present states of the flip-flops, and X. So we'll have, it will be the summation of, that is the min terms of, this is 1 0 0 1, this is value is 9, so after 9 we'll have 10 11 12 13 14 and 15. So these are the don't care conditions. Now let us find out this table. We have to use this state diagram to find out this next state and the output. So here we have for 0 0 0, so this one is 0 0 0. So for this state, whenever input is 0, it is going to 0 1 1, and the output is 0. It means from 0 0 there will be a transition to 0 1 1. Okay, so we have to write here 0 1 1, and the output is 0. Next we have from 0 0 0, when the input is 1, it is going to 1 0 0, and the output is 1. So the next state will be 1 0 0, and the output is 1. Then we have 0 0 1. So for 0 0 1, this is the state. Okay, whenever input is 0, it will remain in the same state, and the output is 0. So we have to write 0 0 1 because it remains in the same state and the output is 0. Next we have present state 0 0 1 and input is 1. Okay, so from 0 0 1, when input is 1, the output is 1 and it goes to next state 1 0 0. Okay, so right here 1 0 0 and the output is 1. Next we have the present state is 0 1 0 and the input is 0. So this one is 0 1 0. When input is 0, the output will be 0 and it remains in the same state. Okay, so we have to write here 0 1 0 and the output is 0. Next we have when input is 1. From 0 1 0, 0 1 0 input is 1. So it will go to 0 0 0 state and the output is 1. So we'll have here 0 0 0 as next state and the output is 1. Next we have present state is 0 1 1 and the input is 0. So from this present state 0 1 1 input is 0. Okay, so it will go to next state 0 0 1 and the output is 0. So it will go to 0 0 1 and the output is 0. Next we have input is 1. From 0 1 1, when input is 1, okay, this one is the input. So input is 1, so it will go to next state 0 1 0 and the output is 1. So it will go to 0 1 0 and the output is 1. Next we have the present state is 1 0 0. Okay, and the input is 0. So from 1 0 0, when input is 0, it will go to, because this one is the input, okay, so when input is 0, it will go to next state 0 1 0 and the output is 0. So it will go to 0 1 0 and the output is 0. Next we have input 1. So from 1 0 0, when input is 1, it is going to 0 1 1 and the output is 0. 0 1 1 and the output is 0. Now we have to find out the k-maps for this next state values. There will be one k-map for each of these columns. Okay, 4 k-maps will have, and we'll have 4 equations for a of t plus 1, b of t plus 1, c of t plus 1 and y. Okay, and after finding out those equations, we have to design the circuit. K-map for a of t plus 1. So here we'll have a 4 variable map. Now we have to fill up this k-map with the values of a of t plus 1. So 0 1 0 1 0 0, 0 1 0 1 0 0. Next we have 0 0 0 0. So 0 0 0 0 0. Then the remaining are the don't care conditions. Okay, because you can see here don't care conditions are 10 11 12 13 14 15. So we have two ones here. Okay, so you can combine like this. So here we'll have a of t plus 1 is equal to, so from this term we'll have a bar b bar, this is x, a bar b bar x. So we have got the equation for a of t plus 1. So this is nothing but dA for the d flip-flop case. Next we have to find out the k-map for b of t plus 1, k-map for b of t plus 1. So here we'll have a 4 variable map again. Now we have to fill up this k-map with b of t plus 1 values. So we'll have 1 0 0 0, 1 0 0 0, then we have 1 0 0 1 1 1, 1 0 0 1 1 1. All are don't care conditions. So this will be one term, this is the second term, and the third term will be this one. So b of t plus 1, that is db is equal to b of t plus 1 equal to, from this term we'll have a, plus from this term we'll have c bar x bar, c bar x bar, plus from this term we'll have b cx, b cx. So we have got the expression for this b of t plus 1. Okay, so db is this one. Now we have to find out the expression for c of t plus 1. K-map for c of t plus 1. Okay, let me draw here itself. So we have to fill up this K-map with C of t plus 1 values. So it is 1 0 1 0 0 0 1 0 1 0 0 0. Then we have 1 0 0 1 1 0 0 1, and these are the don't care conditions. So this will be one term, this is the second term, and this will be the third term. So C of t plus 1 is equal to, so this is nothing but dc equal to C of t plus 1. From this term we'll have a x, plus from this term we'll have cx bar, plus from this term we'll have a bar, b bar, and from these two column we'll have x bar, ax plus cx bar plus a bar, b bar, x bar. Okay, so we have got the expression for dc. Now we have to find out the expression for output y. So k map for y. So here also it will be similar. Now we have to fill up this k map with the values of y. So for y we have 0 1 0 1 0 1 0 1, then 0 0 0 1 0 1 0 1 0 1 0 0. Okay, next will be the don't care conditions. So we can combine like this. So y is equal to, this is a bar x. So we have got the expression for a of t plus 1, b of t plus 1, c of t plus 1, and y, output y. That is, we have found out the next state expression and output expression. Now let us design the circuit. So we'll have three flip-flops, a, b, and c. Okay, so suppose this one is one D flip-flop, this one is the second D flip-flop. Okay, and we have this third flip-flop. Okay, so we have, suppose these three flip-flops, a, b, and c. The input will be, this one is DA because this is a D flip-flop, and here we'll have output is A, this one is B, this one is C. So input will be DB, this is DC. Now we have to give clock pulse to each of these circuit. So here also we'll have clock. These are the three inputs we have to connect now. So this DI is nothing but the next state of A. The next state expression for A is a bar, b bar, x. Okay, and we have input is x. So let me draw, x is the, this is the input line. So if you use an inverter here, so this will be x bar. The expression for this dA is a bar, b bar, x. So take this line. So suppose this one is the A line. Here we have normal output. Okay, and here we have this complemented output, Q complement, or we can say that this is A bar. Here we have complemented output, this is B bar, and here we have complemented output, this is C complement. Now let us connect this. So take a line from here, sorry, okay, A bar line here. Okay, this line is nothing but A complement. So this line we have taken from A complement, so this line will represent the A complement. And suppose this line, one line from B, okay, so this line will represent B. Then we'll have one line from B complement. So take a connection from here and draw a line for B complement. Okay, so this line will represent B complement. Next we have C. Take a line from C and draw an input line. Okay, so whatever we'll have in the functions we will connect from here, these lines. Okay, this is nothing but C, and this line, last one, is the C complement. So draw a line from here. So this is C complement. So this last line is C complement. Now we will find out the expressions. So dA is A bar B bar X. So take a line from A bar, take a line from B bar, and take a line from X. Multiply them. We'll have here a AND gate, and here we'll have the output A bar B bar X. Next we have this DB. Now for B we have A plus C bar X bar plus BCX. So for DB we have to find out the summation of, so here we'll have a adder. So the three inputs will be A plus CX, C bar X bar. So take a line from A, then we have C bar X bar. So let us find out C bar X bar. So take a line from C bar, then take a line from X, C bar X bar, sorry X bar, take a line from X bar. Okay, use a AND gate here. This output will be one input of this OR gate, because we have to add the three terms A plus C bar X bar we have found out. Now we have to find out the BCX. So take a line from B. So this line is B, and from C, and then from X. So use a AND gate. Here we'll have BCX, and this will be the input of this OR gate. Okay, so here we have got this A plus C bar X bar here, and BCX. This is C bar X bar, and this is BCX. So this DB input is this one. Next we have for DC. For DC we have AX. So for DC we have AX plus CX bar plus A bar B bar X bar. So first of all find AX. So take a line from A, take a line from X, use a AND gate, here we'll get AX. Next we have CX bar. Take a line from C, take a line from X bar, and here we'll get CX bar. Next we have plus A bar B bar X bar. So A bar B bar X bar. So take a line from A bar, take a line from B bar is this one, and take a line from X bar. So X bar is this one. So A bar B bar X bar. So use here a AND gate, and here we'll get A bar B bar X bar. Here we have to use a OR gate, 3 input OR gate, and this output will be connected to this DC input. So here we have found out y is equal to A bar X. So A bar X means we have to multiply A bar with X. So we have used here an AND gate, and this line we have taken from here, because this is A bar output. A bar we have taken from here, and X line is drawn from here, and this is the output A bar X. So this is the circuit diagram for the first part of the problem. Now as per the problem, we have to find out, we have to determine the effect of the unused states. Now we have to use the expressions of A of t plus 1, B of t plus 1, and C of t plus 1, that is the next states of the present states A, B, and C, and find out using the equations, that is the equations we have just found out. So let us find out the next states using the equations. So previously we have assumed it with don't care conditions. Now let us find out the next expressions. So process will be similar, present state, then we have input, next state, okay, and output. So present states are A, B, and C. Here we will consider only the remaining, that is from 10 to 15. Okay, so input is X. So previously we have found out up to 1 0 0 1. So now we have to find out from 1 0 1 0 to 1 1 1 1. So 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. So let us find out the next steps using the equations. So the equations for a of t plus 1 is a bar b bar x. That means whenever we have x equal to 0, this will be 0. Okay, so here we can see that this x is 0, so it will be 0. This one also x is 0, so 0 and 0. So for these terms, a bar b bar will be 0, so it will be 0, and a bar b bar is 0, so it will be 0, and a bar b bar is 0. So all are 0. Next we have to find out for b of t plus 1. So b of t plus 1 is a plus c bar x bar plus bc x. So we can see that when this is in OR operation, so whenever any of the term will be 1, the output will be 1. For all of them, a is equal to 1, so it will be 1. Next we have to find out for c of t plus 1. So for c of t plus 1, we have this expression. So ax plus cx bar plus a bar b bar x bar. So you can easily find out using this expression. So let me write down directly. So we'll have here 1 1 0 1 1 1. Output expression is a bar x. Output expression is a bar x. So whenever x is equal to 0, the output will be 0. Okay, x equal to 0 0. Then a bar, let us find out, a bar will be all 0. Okay, so it will be 0. So all the outputs are 0 here. Now if we draw the state diagram, what we'll have, suppose we have this states 1 1 1, this is one state. Suppose 1 0 1, this one is the second state, suppose, and suppose this is the remaining state, so 1 1 0. Whenever the present state is 1 0 1 and the input is 0, so it is going to 0 1 1. So let me draw here 0 1 1. So there will be a transition from 1 0 1 to 0 1 1. So 1 0 1 to 0 1 1. So there will be one transition. Okay, so for the one case also we have the same transition. So here we'll write here for input 0 and output 0, the transition is from 1 0 1 to 0 1 1, and for input 1 also the output is 0 and the transition is the same. Next we have from 1 1 0. So from 1 1 0 we'll have a transition to 0 1 0 and 0 1 1. Okay, so 0 1 0. So this is one state. So here we'll have, so for input 0 we have a transition from 1 1 0 to 0 1 0. So 1 1 0 to 0 1 0. Okay, for input 0 and output 0, 0 by 0. Next we have transition from 1 1 0 to 0 1 1, and the input is 1, output is 0. So 0 1 1 is this one, so we'll have a transition from 1 1 0 to 0 1 1, and the input is 1, output is 0. Next we have the present state is 1 1 1, that is this one. Okay, and for both the inputs for 0 and 1, the next state is 0 1 1 0 1 1. So it will go to 0 1 1 1 for input 0, output is 0, input 1, output is 0. So input is 0, output is 0, input is 1, output is 0. So here we can see that for all of these remaining three states, okay, these three states results in 6 don't care conditions that we have used in the K-maps. Okay, here we can see that they are transiting to 0 1 1 and 0 1 0, but here we can see that we already have this 0 1 1 and 0 1 0. So we can write here the machine, the state machine or machine is self-correcting because of those don't care conditions. Self-correcting because of the given don't care conditions, that is for the unused. So these are the three unused states. Unused states, the transition is to the known states. So here we can see that for these unknown states, the transition is to this known states, because these 011 and 010 we have already in the first table. Okay, these are the known states, it is given in the state diagram. Okay, so this circuit is self-correcting. Now let us go to our second part of the problem. So in the second part of the problem, we have to use JK flip-flops in the design. The process will be same. So we have already found out the present state and next state. Okay, now we have to find out the respective JA, KA, JB, KB, JC, KC, and the output Y. Okay, and after finding out, we will design the, or we will draw the circuit. Now let us find out the excitation table. So here we have is present states, then we have input, then we have next state, and then we have flip-flop. This is FF, means flip-flop inputs. So these values I am just copying from this table. Okay, so this present state and next state values I will be writing from here. These are the present state and this will be the next state. Okay, these are the present state, these are the next state, just let, and these are the inputs. Okay, so let me write down this portion of the part and then we will find out the inputs of the flip-flop. Okay, so let me write down A, B, C, X, A of t plus 1, B of t plus 1, C of t plus 1, and flip-flop inputs are JA, KA, JB, KB, JC, KC. So we have the present state and input are 0, 0, 0, 0, 0, 0, 0, 1. Next we'll have 1 0 0 0 1 0 0 1. So up to here we have to find out, because these are the given states as per the state diagram. Now we'll write down the next state from the first state table. Okay, from this state table we will find write down this one. So here we'll have 0 1 1 1 0 0 0 0 1 1 0 0 0 1 0 0 0 0 0 0 1 0 1 0 0 1 0 0 1 1. So we have got this present state and the next state values, and using the excitation table of JK flip-flop, whenever the present state and the next state both are 0 0, J is equal to 0 and K is equal to don't care condition, the JA and K value will be 0 don't care. Okay, so for 0 0 this one also 0 don't care, so 0 0 0 don't care. So for this one 0 don't care. So here also we have 0 0, so we'll have 0 don't care. Here also 0 don't care condition. So for 0 1, so for present state 0 and next state 1 we'll have the 1 and don't care condition. Okay, for 0 1 1 and don't care condition, and next we are remaining with 1 0 and 1 0. So for both we'll have, for 1 0 we'll have x 1 don't care and 1, and then don't care and 1. Okay, for 1 0 we have, this is using the excitation table of JK flip-flop. Now let me directly write down this JB, KB and JC, KC values. So for B and B, so for 0 1 we will have, so for suppose 0 0 we'll have 0 don't care, so 0 0 0 don't care, we have 0 0 0 don't care. Now for 0 1 0 1 we'll have 1 don't care. Next we have 0 1 here, so 1 don't care, so 1 don't care. Next we have 1 1, for 1 1 we have don't care 0, so for 1 0 we have don't care 1, so 1 0 don't care 1, so for 1 1 don't care 0. Now let me write down for JC, KC. So for C, this third column we have to see, and the seventh column we have to see. Okay, so we'll have 0 1, for 0 1 we'll have 1 don't care, So 0 0 means 0, don't care. So 1 1 means don't care, 0. 1 0 means don't care, 1. So for 0 0 means 0, don't care. 0 0 means 0, don't care. So for 1 1 means don't care, 0. 1 0 means don't care, 1. 0 0 means 0, don't care. 0 1 means 1, don't care. So we have got this excitation table. Now we have to find out the expression for JA, KA, JB, KB, JC, KC using K-maps. K-map for JA. So here we'll have a 4 variable map. So we have a 4 variable map here. A, B, C, X. 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. Okay, so these are A, these two row are B, these two column are C, these two column are X. Now we have to fill up this K map with the JA values. So for JA we have 0 1 0 1 0 0 0 1 0 1 0 0 0 1 0 1 0 0. Then we have 0 0, don't care, don't care. 0 0, don't care, don't care. Then all this remaining are don't care conditions. So there will be one term. Okay, so this will be the one term. So JA is equal to, so this will be B bar and X. B bar X. Now we'll find out the KMF for KA. So for K, we have to put these values. So K values are don't care, don't care, don't care, all are don't care. Then here we have 1 1. So these are all don't care conditions. We have 1 1 here, and we'll have these don't care conditions. So here we can see that we can select the whole table. So if we select the whole table, Ka will be equal to 1. Now let us find out for JB. Now we have to put the values of JB. So for JB we have 1 0 0 0 XX, 1 0 0 0 don't care, don't care. Then we have 1 0 0 0 don't care, don't care. Then we have don't care, don't care, 1 1. Don't care, don't care, 1 1. So these remaining are don't care conditions. So this will be one term. Okay, and this will be the second term for this one. So we'll have JB. JB is equal to, this term is A plus, from this term we'll have C bar X bar, because this 0 0 will have C bar X bar. Okay, so this is the expression for JB. We have got the expression for JA, KA, JB. Now we have to find out the expression for KB. So we have to fill up this K-map with this KB values. So KB we have don't care, don't care, don't care, don't care, 0 1, don't care, don't care, don't care, 0 1. Then for KB we have 1 0, don't care, don't care, 1 0, don't care, don't care. So all are remaining are don't care conditions. So this will be one term, and this will be the second term. So KB is equal to, from this term we'll have C bar X, C bar X plus C X bar, C X bar, or we can write it as C XOR X. So this is XOR operation, C XOR X. Now let us find out the KMF for JC. So we have to put the JC values here in this K map. So JC values are 1 0, don't care 0 0, 1 0, don't care 0 0. These are don't care conditions. Okay, don't care and 0 1. So this one is 0 and this value is 1. And the rest are the don't care conditions. So this will be one term and this will be the second term. So JC will be, so from this term we'll have a x plus, from this term we'll have a bar b bar, this is x bar. Okay, now we'll find out the K map for KC. Okay, now we have to fill up this K map with KC values. So KC values we have don't care 0 1, don't care 0 1, don't care. Then we have 0 1, don't care 0 1, don't care. Okay, so here we'll also have don't care conditions. So we can combine like this. So there will have only one term. Okay, one min term. So KC is equal to, this is nothing but x. So we have got the expression for JAKA, JBKB, JCKC. Okay, and we already have the expression for y is y equal to a bar x. Now we have to use these equations for drawing the circuit. Similar to the previous case, we will have three flip-flops. A, B, C. So this is flip-flop A, this is flip-flop B, and this is flip-flop C. B flip-flop, this is KB. So in the second part, we have to use JK flip-flop. So here we'll have JA, KA, JB, KB, JC, KC. So these are the three flip-flops. Here we'll have the normal output and here we'll have complemented output. This is A bar, B, B bar, C, C bar. Okay, so these are the three flip-flops we have to use. We have one input is X, so we'll have here one input that is X. So we'll have here one input line, that is this line is for X, that is the input. So we'll use here an inverter. So here we'll have X bar. In the expressions of JAK, JB, KB, JC, KC, we have A as well as A bar. So draw two lines. So from A, draw a line. So this is A. So from A bar, draw another line. Okay, so this will be A complement. Similarly, in the expressions of JAK, we have B bar. Okay, we have only B bar. Okay, so you need to draw only one line from B bar. Okay, so take a line from B complement. Okay, and define it here. This is B complement and this one is A complement. So similarly for C, we can see that C bar is there and C is also there. Okay, so we have to draw both the lines. That is, one will be from C. Okay, so this is C. Next we have C bar. C bar is from here. Take a line and this line is C complement. Now we have to see the expression for JAKA, JBKB, JCKC. JA is B bar X. So find here B bar X. Multiply them. B bar is this one and X is this line. You say AND get. Okay, so here you'll get B bar X. Okay, so directly connect here. Okay, and KA is equal to 1. So you can directly give here a active high input, that is 1. Here also you will have to give clock. These three ports will be connected. to the clock signal. So these three are clock. Next we have got the expression for JAKA. For JB we have A plus C bar X bar. JB is A plus C bar X bar. So take a line from A, C bar X bar. So take a line from C bar, take a line from X bar. You say AND get. Here we'll get C bar X bar and add these two with a OR gate and give it to the JB input. Okay, so here we'll have A plus C bar X bar. Next for KB we have C XOR X. Take a line from C, this one is C line, and take a line from X, use a XOR gate and connect to this KB input. So this is C XOR X. So we have got this JAKA, JBKB. Okay, now we have to connect this JC and KC input lines. So for JC we have AX plus A bar B bar X bar. So we have to find out AX. So take a line from A and take a line from X. You say AND gate, here will get AX, okay, plus A bar B bar X bar. So take a line from A bar, take a line from B bar, this one is the B bar line, X bar. So X bar is this one. So you say AND gate. So here will get A bar, B bar, X bar. And you have to add these two to get the JC. You say OR gate. These will be the two inputs and this will be connected here to this JC. And for KC we have KC is equal to X. Okay, so directly we can connect the KC port to the X input line. Okay, so this KC will be directly connected to this X input line. Okay, so we have got all the JAKA, JBKB and JCKC. Now we have to find out the expression for Y. So Y is A bar X. So A bar is this one. Take a connection from X similar to the previous case. Okay, you say AND gate. Here we'll get Y is equal to A bar X. So this is a AND gate. So this is the circuit diagram for the part 2 of the problem. Now we have to write the effect of the unused states. So here we'll have to write the machine is self-correcting. It is similar to the previous case, okay, self-correcting because Ka is equal to 1. So this is the complete solution of the problem number 5.19 from the chapter number 5. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.